Okay, so this next section is going to look at blood flow, blood pressure, resistance, and the different relationships. So as we get started, there's a couple things to keep in your mind. Flow rate, right, is dictated by pressure differences. Pressure difference is, how we're going to show it scientifically, is with what's called a delta P. That little triangle means change in, okay? So that pressure difference is important. We'll kind of look at that concept a little later. Let's start out with a couple definitions, though. Let's look at pressure. So pressure, which we indicate as a capital P, typically, right, is the force exerted by a fluid on the container holding that fluid. That fluid is a scientific fluid. It means it's not stationary. So this would include both, so the fluid would include both a liquid and a gas for our purposes. And so this again is to sort of remind you also that we should know these numbers. The left and right atrial pressures, right, are 5/0. So systolic is 5, diastolic is 0. The right ventricle is 15/0, and the left ventricle is 120/0. What this shows here is the drop in pressure. So here's the pressure over here, okay? And this shows the drop in pressure as we move through the vascular system. Notice that we have pulse pressure here, here. We also see it actually in the heart as well. It's not called pulse pressure. And we see these pressure differences by the time we get to the capillaries here, that it no longer has a systolic and diastolic pressure, and it's one continuous flow because there is no difference. And again, this assures that we get better oxygenation of our blood as it flows through the lungs and better delivery of oxygen as it flows through our systems. So going back to the idea that flow is pressure differences, right? Here's kind of a nice little exercise to look at that. So here is a blood vessel, and this blood vessel at the one end has the total pressure of 100 millimeters per mercury, and at the other end it's 75. So the difference in pressure, the delta P, right, equals the difference between these two variables, 100 minus 75, so that's 25 millimeters per mercury. Remember, we're going to measure flow, any pressure in this class, always in millimeters of mercury. Sometimes in a clinical situation, they might measure a pressure in centimeters of water, especially in terms of a pulmonary function thing. But generally speaking, if we're talking about pressure, we're going to be millimeters of mercury. Here's another vessel. Notice it's the same length, same width or diameter. And its pressure at the one end is 40, and its pressure at the other end is 15. Right? So just like the top one that moved from a high to low pressure, right? Blood went from left to right. This one's going to go from a high to low pressure, left to right. But if you look at, again, the pressure difference, even though the total pressure is significantly less in both of these variables, right? The delta P is still 25. Since this one's 25 and that one's 25, right? And they're equal, the flow between those is going to be equal as well. So it's the pressure difference that matters, not nearly as much as the actual total pressure. So the pressure difference is a much greater variable in terms of determining flow than the total pressure. Now there's a nice relationship between variables. It's sometimes known as the ohmic relationship, and for some of you that have studied other things like electricity in other classes, might have learned the Ohm's Law, which basically says V equals IR. So the voltage of, and this is, looks at electrical circuits. So it's probably something you learned in physics maybe. So voltage equals the current times the resistance. That's what V equals IR actually stands for. We don't have to worry about Ohm's Law per se, but when we talk about the cardiovascular system, the functional name is called the circulatory system, and that's because blood circulates. So it's a circuit. It's the same principle as an electrical circuit is. And so instead of having V equals IR, we can put it into the similar variables, though. We're going to say pressure, that would be equivalent to voltage, equals flow, that's the current, times resistance, that's the resistance. So our general formula is pressure equals flow times resistance. Now, we've already stated that by convention, we use capital P for pressure. We use capital R for resistance. And this is another one of those variables where flow becomes, they don't want to use F because it's function, right? So they use some other letter and they use Q oftentimes. Now that gets confusing because we saw earlier this semester that Q was an example used in terms of heat sometimes. But we're going to do this. So this makes it a little bit easy if you think about it. So pressure P equals flow Q times resistance. So if you know the alphabet, right, then you just go P, Q, R, right? So P, Q, R, and you just put the equal sign after P. So pressure equals flow times resistance. That's a pretty easy way to remember that formula. And this is going to be very important. You should memorize this, you put it in your head, and we'll see applications of this a couple times. In addition, mathematically, you're going to have to be able to either manipulate this equation. So if we wanted to look at flow, right, we would divide both sides by resistance, right? So let's erase this, right? And so if I want to get flow, I can divide both sides by resistance, right? So this is R and this is R, right? And so this, because R over R equals 1, we can get rid of that. And so flow equals pressure over resistance is the way to do it. And we could do the same thing for resistance if we wanted to calculate resistance. So that is a very handy equation that'll come in handy multiple times this semester. So it's one of those ones you should learn, and the derivatives from it. So P equals QR is the best way to think about it. Okay, so now we're going to spend a little bit of time talking about the variable of resistance. Resistance is very important to understand in terms of the human body, and certainly resistance will affect blood flow, right? And so a long time ago, a scientist by the name of, people say his name differently, most people call it Poiseuille, although I understand that's not the way to pronounce it. Some people say Poissier and all sorts of other derivatives, but Poiseuille looked at resistance in tubes and tried to look at what affects the resistance in tubes. That becomes important for us in physiology because our blood vessels are really just tubes, and those tubes add resistance to flow. So let's kind of look at the relationship between these variables, okay? So resistance depends on a couple different factors. One is tube length, right? So the longer the tube, the greater the resistance, okay? So we're going to call tube length L, capital L, all right? So as an example, looking at this photo here, right, this picture, this straw on this side, right, has a small tube length. This straw has a huge tube length. So the long straw is going to have an increase in resistance because of that. And basically, if you think about it, as fluid travels through the straw, it's going to make contact with the inside of the straw, and that's going to create friction. So the longer the tube, the greater the resistance. So if we increase L, that's going to increase big R, resistance, right? Now, the second factor is viscosity. Now, we can't use V for viscosity because that's a whole bunch of different things, but oftentimes in physics, especially velocity and things like that. So they use this kind of handwriting N, right, symbol. And so viscosity refers to the thickness of the fluid. Okay, so as an example, if you drank through a straw, which would be the same length, right? So if we drank through a straw, drinking soda or iced tea, that would have a lower viscosity than drinking through a straw that had a shake, like a milkshake or something. And so that's why they have it right here. And we say, I drink your milkshake, is getting into the idea of viscosity, right? And so as the fluid gets thicker, it would be harder to move it through this straw, right? So we're going to say if we increase the handwriting N, right, it's going to increase R again. So both of those are directly proportional. If length goes up, resistance goes up, and if viscosity goes up, resistance goes up. The third factor, which by far is the most important, and we'll kind of get to that idea in a second, is tube radius. Now, if we looked at a tube, and I'll draw it up here, right? So here's my tube, all right? We can measure two things. We can measure all the way across from one side to the other, right? That's the diameter. Or we can measure from the middle just to one side. That's the radius. Okay, so the radius and diameter, while they're not the same thing, are proportional. If I double the diameter, I have to double the radius. But the value that's most important to us is the radius. So for radius, since we can't use a capital R, because capital R is resistance, right? We see it right here. We're going to use a small r. And what happens for the tube radius is as the tube gets larger, right? So if we looked at two tubes, we'll look at a tube that's got like a radius that's like that and a radius that's like that. It's pretty obvious that the tube with the smaller radius, the first one, it would be more difficult for fluid to get through because we have more resistance. And so the tube right here with this nice wide diameter, this nice wide radius tube, is going to have less resistance. And so this is a little different in terms of how this works, because if we said, if we increase the small r, the radius, right, that's going to actually equal a decrease in big R. Okay, so this is inversely proportional. And a long time ago, Poiseuille recognized these things and put it together in what we call Poiseuille's law. And it basically says big R, and don't worry about the 8, right, equals L times N, so the length times the viscosity, over the radius, but here's the key, to the 4th power. Right? So big R equals 8L times N over R to the 4th. That's what Poiseuille's law is right there. Okay? So understanding Poiseuille's law is very important, and let's kind of go back and look at it for humans. So I'm going to erase all this stuff, and we'll look at this again. So which one has the most effect on humans? Well, there's a couple reasons why radius ultimately does. We can't forget about length and viscosity because they do play a role, but from a control standpoint, the human body doesn't change the length of your blood vessels to change the resistance, right? And so, maybe if you had an arm or a leg cut off, right, you'd obviously change the length of your blood vessels, and that would change resistance. But your leg or arm would just fall off to control resistance, right? It changes very little in humans. There's some evidence that as people gain weight, they get an increase in the capillaries and the blood vessels that serve the increase in the adipose, and that tube length increases resistance is one of the reasons why some scientists believe that people that have higher body weights, higher percentage of body fat, would have a greater potential for hypertension. It's because of that increased tube length, and that increases the resistance. So to overcome that, we have to increase the pressure. All right. So that changes very little in humans. We can't forget about it, but it changes very little. So that has a little bit of an effect. Fluid viscosity plays a role. How thick is your blood? Okay. And if the blood gets thicker, that's going to increase in resistance. And in humans, the changes tend to be pretty slow. If you want to change the amount of your albumins, remember that was the key protein that was an osmotic regulator, but made up more than half, probably about 60% of your blood proteins. Or we had something called polycythemia, right? So poly, many, cyth would be cells, and emia would be blood. So somebody who had polycythemia would have too many cells, and typically this is reserved for red blood cells. So if you have an excessive number of red blood cells, that's going to make your blood thicker, and that's going to increase the viscosity. So if that happened, then to compensate for that, you would have to increase the pressure because the resistance goes up, so the flow would stay the same. But that happens. You can see the same thing with the albumins in your protein, or you could go the other way and effectively increase those things by having less plasma, so through dehydration. All three of these things, though, take a while to have a change. You just can't increase the number of protein you have. You can't just suddenly, dehydrate your body, or you can't suddenly have too many red blood cells. So these tend to be fairly slow processes, and certainly not that important for the second-to-second, minute-to-minute regulation of resistance. So it all comes down to this one, and this is the big one, tube radius, so the small r. There's a couple reasons why this is important, but the big one is, there's actually two big ones, I guess. One is we can change tube radius very easily, very quickly. So by changing your sympathetic tone, increase the number of action potentials or decrease the number of action potentials to your arterials would change the tube radius. Circulating levels of hormones, if you released a whole bunch of epinephrine right away, that would cause constriction of the arterial, so the tube radius would go down. The number of factors, the local autoregulation that cause vasodilation by local chemicals would change the radius. And that's, literally released, and within seconds, we have an immediate change. So that's one of the things. It changes very quickly. The other portion of this is the small changes in radius have significant effects in terms of resistance. And that's because, again, looking at this equation, the resistance is raised to the fourth power. Okay, so just as an example, if we doubled the tube radius, so if we double the tube radius, so if we increase the R times 2, so if we double that tube radius, what happens to resistance? Well, there's a couple things. Since small r, radius is on the bottom, and big R, radius on the other side, is on the top, they're inversely related, right? So if the radius goes up, let me erase that and do it right. If we increase small r times 2, right, big R would be resistance. If we increase small r by 2, what actually happens to resistance? Well, remember, this is raised to the fourth power. So this would be 2 to the fourth power, which would be equal to 2 times 2 times 2 times 2. So that is 4, 8, 16. So this would have a 16 times change on resistance, and since radius went up and they're inversely proportional, this would have a 16 times decrease in big R. So 16 times decrease in big R. So that's the significance of R to the fourth power. All right. The other problem is, and I can't use these erase things too much, these highlighters, because it quickly uses all the memory in the computer. But what we can do then is another very important application of this is to combine the last two equations that we sort of learned. So we learned that P, right, pressure equals flow times resistance, right? So P equals QR. So then we could say that Q, and to isolate it, equals, and again, we just did this the other slide, right? We just divide both sides by R. So pressure, oh, it's right here. I'm trying to write it out. So flow equals pressure over resistance, right? So now what we're going to do is we're going to take this big R right here, zoom out again. So what we're going to do is we're going to take this big R right here, right? And we're going to put it right here. But now we're going to take this equation for big R and move it over here as well. So since here, for this equation, big R is on the bottom, we're just going to flip this upside down. And so our flow equation, right, one of the more useful ones is this one right here. Pressure times radius to the fourth power over length times viscosity. All right, and being able to look at this formula, because we're more often physiologically worried about flow, so to put it in terms of flow, that's important. So if I said, okay, what would happen to flow if pressure doubled? Well, if pressure doubled, the difference in pressure doubled, it's directly proportional, flow would go up. What would happen to flow if viscosity doubled? Well, since viscosity goes up, it's inversely proportional, so flow would go down. What would happen if we doubled pressure and doubled viscosity at the same time? Well, it would be 2P over 2N, and the 2's would cancel each other out, and it wouldn't change at all, as an example. So those are the types of things that you have to look at in terms of figuring out the relationship between pressure, flow, and resistance. All right, so we've seen the equations, pressure equals flow times resistance, and then rearranged it for flow equals pressure over resistance, and we've seen the effect of that. When we talk about flow, we're not talking about the velocity, we're not talking about how fast blood moves, we're talking about what's the volume of blood measured in mils per minute. All right, we'll kind of see that in a little while as well, how we deal with that. So one of the things we can look at when we look at the relationship between pressure, flow, and resistance is a branch of science called hemodynamics. So hemo refers to blood, dynamics is how it moves basically. And it really looks at the difference between flow, pressure, and resistance. All right. And again, we maintain pressure in order to maintain flow. So there's that relationship. It's believed that we actually maintain pressure, that's the homeostatically regulated variable, not flow, because it's easier for us to measure changes in pressure physiologically than it is changes in flow. Some scientists argued for a long time that the human body could never sense flow, and so we had to use pressure. But there's some recent evidence that we have some potential flow receptors in the kidney, so it is possible, but it's probably easier for us to measure pressure, and pressure determines flow, right? So if I change pressure, I'm going to change flow. If I change resistance, I'm going to change flow as well. All right. So just to kind of look and say, okay, if I wanted to increase blood flow, so let's say that you're going to get up and run, right? We're going to have to send more blood to your legs to supply the energy and supply the oxygen to the muscles in your legs for you to continue exercising, okay? So the average person, if you went from sitting to running, that increase in blood flow might be easily 10 times, all right? So if I wanted to increase blood flow 10 times to the legs, how could I do it? Well, let's kind of look. If I did it by the increase in pressure, right, these are directly proportional. So to get a 10 flow increase, right, and leave resistance alone, but to get a 10 flow increase in blood flow through the leg, I would have to have a corresponding increase in terms of pressure. I'd have to have a 10-fold increase in blood pressure. So literally, your blood pressure would have to go something like from 120 over 80 to 1200 over 800. It wouldn't work exactly that way, but you get the point. We just can't change pressure that much. Literally, our head would explode if we did. So it's inefficient, and it requires a large change in pressure, and large changes in pressure, especially over time, cause physiological damage. So we can't increase flow appreciably by changing pressure, right? What about changing the resistance? Well, the length and viscosity we spent a little bit of time talking about, it's slow. If I want to change the length of my blood vessels to increase pressure, right, I would have to change the length. That would take a while. Same with viscosity, right? And again, if I increased length, that would decrease pressure because they're inversely proportional, right? If I increase length, that would decrease flow, right? So, and then the same with viscosity, and viscosity would take a while. So I can't immediately change my blood pressure to change my blood flow at all because of the high need for the differences in pressure. And I cannot change my length or viscosity appreciably, and especially fast enough to have an effect on flow. So the only thing that's left is changing the radius. And again, the radius is the way we primarily control blood flow and blood pressure because it's rapid, it's potent. I can do it at various points in my body, so I can constrict a vessel in my gut while I'm dilating a vessel in my leg, right? And so if I have constriction of an arterial, it'll decrease flow. And if I have a dilation of an arterial, it'll increase flow. So that's called the hemodynamics. So if you remember, it's the pressure differences that drive blood flow, right? And as we look at this little figure, there's a whole bunch of information on it. It talks about the systolic blood pressure. Remember, that's when we're contracting. It talks about the diastolic blood pressure. That's when we're relaxing. When we talk about blood pressure, unless we specify otherwise, invariably, whoever is specifying that information, right, is talking about arterial pressure. If they're going to talk about venous pressure, they would precede it with venous pressure, all right? So as a reminder, some of the values we've learned before, the aorta has a pressure. That's what we try to estimate with a blood pressure cuff, like in a clinical setting, of about 120 over 80. Your pressure of your vena cava, that's the pressure going back to your right atrium, it's about 4 to 8 millimeters of mercury. The right atrial pressure is about 5 over 0. Remember, during systole, it goes up high as 5, and during diastole, it relaxes down to 0. And your pulmonary trunk, right, has a pressure of about 15 over 5, right? So one of the things that we want to know oftentimes in situations like this is what is the average blood pressure over time. And that average blood pressure over time is called the mean arterial pressure. So we see it right here, the mean arterial pressure, okay? It's not calculated the way you think because it has to do with the time. And we mentioned this on a previous video, that when we looked at the ECG wave clearly shows that on average, humans at rest, that have a resting heart rate, spend about 1/3 of the time in systole and about 2/3 of the time in diastole. So we have to weight that when someone is resting. And so the mean arterial pressure formula, we just call it MAP, equals 1/3 of the systolic pressure plus 2/3 of the diastolic pressure. Okay, so 1/3 of systolic plus 2/3 of diastolic. So to get there, let's say that this person had a blood pressure of 120/80. So if I want 1/3 of 120, all right, so 120 divided by 3, that's 40. Two-thirds of 80 is a little more difficult, but if you take 2/3 of 80, two-thirds of 80 is going to be equal to, if I do that math, it would be 53.3. Can't make threes very well on this. 53.3. So we just add these two together, 40 and 53.3, and we get a mean arterial pressure of 93.3. Okay, pretty easy calculation, except the problem is students often have problems with it, and they often flip-flop the systolic and diastolic and things like that. So what I find an easier formula is the pulse pressure, using the pulse pressure formula. Okay, so in order to get pulse pressure, we just take the systolic and diastolic blood pressure difference. So in the case of, again, 120/80, right? So if we take that difference, it's going to be 120 minus 80, and that's going to equal 40. Okay? So that's pulse pressure. Now to get the mean arterial pressure, we're going to use a different formula. It's going to be 1/3 of the pulse pressure. That has the unfortunate scientific designation of PB, right? Plus the diastolic pressure. So 1/3 pulse pressure plus diastolic. So to get to mean arterial pressure, right? So this equals mean arterial pressure, MAP. MAP. So this one's pretty easy. It's much easier to calculate. 1/3 of 40, so 1/3 of 39 would be 13, so plus a third. So this would be 13.3. That would give me 1/3 pulse pressure. Diastolic, I don't have to do any math. It's already there. I know it's 80. So this would be 80. So 13.3, run out of memory, plus 80. And if you go back and look at what we had before, it would give us the same 93.3 no matter how we calculate it. So I like that formula better. Pulse pressure is not a bad variable to have anyway, and it's an indication of stroke volume. The higher the pulse pressure, the greater the stroke volume tends to be in a person. So that's what we're looking at for the pressure. So again, that's the pressure differences and how they drive blood flow. Okay. So one of the things we can look at is ventricular performance, and that's really looking at how effective is the heart as an actual pump. All right, so some of the formulas that you would find useful, right, would be the stroke volume formula. We saw that before, right? So stroke volume equals N diastolic volume minus N systolic volume. Okay. That was from the cardiac cycle. Pulse pressure we just did is systolic blood pressure minus diastolic blood pressure, so it's the difference. The EF stands for ejection fraction. Okay, so that's how much blood do you spit out of the heart over how much you had total. So that's stroke volume divided by end diastolic volume times 100. So like a typical one is, we said a stroke volume typically is 70. We said a good number for end diastolic volume is 100. We put it at 100 to make this calculation easy, at least part of the reason why. So 100, 70 over 100 is 0.7 times 100% is 70. So we're getting an ejection fraction of 70%. That's pretty normal in people, meaning they only pump out 70% of the blood they have available in their ventricle when it contracts. We've talked about cardiac output before in class. Cardiac output is stroke volume times heart rate. So that's a way to measure cardiac output. All right, and here's some examples of cardiac output. Someone who's resting, a healthy person, it's about 5 mLs per minute, about 70 beats per minute and 70 mils per beat. That gives me a cardiac output of about 5 liters per minute. During exercise, your heart rate may go up to 150 and or 200 even at max, and the stroke volume is 150. So if you had something like that, you'd go from 5 liters per minute up to 300 liters per minute. Sorry, 330 mils per 30 liters per minute in terms of cardiac output. So a 6 times increase from rest. And someone with a cardiac patient, they might have that low heart rate. Remember, we call that bradycardia for the low heart rate. At 40, and then a low stroke volume of 25, and 25 times 40 is about 1,000 mLs, or 1 liter per minute. So you can see cardiac output can vary significantly between different people. The other equations that we have and looked at was the pressure, so P equals QR, right? If you look at this general formula, we can call the flow the cardiac output, and the resistance, we can make it specifically total peripheral resistance. So if we replace that equation, we get mean arterial pressure, right, equals cardiac output times TPR, total peripheral resistance. So it's just a flow times resistance. And we said earlier, cardiac output equals stroke volume times heart rate. So mean arterial pressure can equal stroke volume times heart rate times TPR. So these are the other two formulas I want you to understand and know as well. So for mean arterial pressure, then we have a whole bunch of different ways to measure it, and it really depends on what variables we have as to what equation we will use. And this is the key, is mean arterial pressure equals stroke volume times heart rate times TPR. Okay, so this is one of the most important equations we do this semester, and we'll look at it in some detail, and we'll look at how this mean arterial pressure is homeostatically regulated through stroke volume, heart rate, and TPR. All right, so that'll be our next video.